All right, let's get started with today. So before I forget, for those of you who attend this tech symposium, you get extra credit. That's Thursday, right? The tech symposium. Friday. Okay. That Wednesday we don't have class. So that project update is gonna be through email. All right. So take advantage of that. It's to encourage every one of you to go there. In order to get the extra credit, you have to sign. So Kayla, anyone knows Kayla? The department, Kayla Jimenez? Yes. So you have to sign in with her. If you don't sign in with her, you don't get the credit. All right? Make sure that you attend. It's fun. It's a cool way to network and create like some cool interactions with people that work in the industry or academia, whatever. So it's great to have fun there. So I hope every one of you guys go there. Yeah, you just sign with her because it's the only way that I can get the sign sheet. So I don't have any other way to know if you were there or not. Right. Sorry? The tech symposium next Friday. November 18th. Yeah. Okay. As I said, if some of you wants to meet with me, not on Wednesdays, but on a different day, uh, what works for me best is office hours. All right. So if you want to meet during my office hours and then give me the update of the project, I'm happy to do that. All right. In case you don't want the quick interaction that we have in here. All right. If some of you need more time, please shoot me an email and then we can arrange from there. Okay. Um, Today we're gonna do some cool modeling. All right. We're gonna do 3D modeling, not a plate, because we've been doing a lot of plates. So we're gonna do something that we see in the industry a lot, that is called pressure vessels. So you use this for oil and gas, for storage of gas. This cannot be also like extrapolated to thick wall cylinders. So whenever you have a pipe that's treated as a thick or thin wall cylinder, and depending on that, you assume some conditions. Those problems generally you can solve them by hand. So there are some known solutions for those problems. However, as you start adding physics to a problem, such as heat transfer, such as plasticity, those solutions are no longer available, right? The easy solutions that you can derive by hand are usually for linear elastic materials. So today we're gonna do that. We're gonna create a complicated problem where we have heat transfer. It's not gonna be transient heat transfer. For some of you who want to see the thermal stresses evolving during time, that's called transient heat transfer. Today we're gonna focus on the steady state. So what is the steady state? Whenever you apply some conditions, heat transfer conditions, and then what is the final state of the structure after many hours have elapsed, right? And supposing that nothing changed in terms of the boundary conditions. So that's called the steady state of a heat transfer problem. We're gonna add plasticity. So finally, we're gonna see some yielding in our pieces. And we are gonna learn how to do 3D symmetry conditions, right? Because as we're gonna see, this takes a little bit of time to solve. So if we can take advantage of any symmetry in the problem, we definitely need to do that. Okay, so for those of you who just arrived, Tech Symposium, if you go and sign, extra credit, all right? So, as I said, we are gonna be modeling pressure vessels, all right? So usually what we do is we cut it in half, all right? And when we cut it in half, we have this sphere, or like only the top part of right part, or whatever you want to say, part of the sphere. However, we can add another symmetry to the problem and cut with this red plane in here that we have. And at the end, you only model 1/8 of the structure. This is gonna save a ton of computational times. is not linear. So if 1/8 of the problem takes 10 seconds to solve, the whole problem is not going to take 80. It's going to take way more. The solvers that solve this system of equations, they don't work linearly. If you have more degrees of freedom, it's exponentially. So the more degrees of freedom of your problem has, the more computational time is going to have. All right. So we're going to do this sphere. I'm not going to care a lot about the dimensions today. I want to add a lot of physics, the material properties. We are going to add some heat transfer properties. We are going to add some plasticity properties. So I'm going to focus on that more than in the modeling, right? Because for what I've seen, everyone is a little bit of knowledgeable in SolidWorks or in these modeling techniques. So I'm going to focus more on the complicated physics, which is the plasticity and the heat transfer in here. I'm going to use this table later because properties, we have to be super consistent here with the properties. All right. So let's get started. The first thing that I'm going to do is to create a folder. For me, it's going to be called Abaqus 3D Plasticity. I'm going to copy that folder location, and I'm going to set my working directory. All right. So I'm going to create a part. I'm going to call it a sphere. A sphere 1/8. All right. It's going to be 3D, deformable, and I'm going to use a revolution technique in order to create this. The dimensions, let's work in millimeters. I don't care about the dimensions too much here, but so yeah, let's say that yeah, 200 is fine. Okay, so I'm gonna model. First, let me go here to tools, customize, no, tools. I always forget. Options, view manipulation, and SolidWorks. So I'm gonna create 2 circles. These are gonna be my 2 circles. The first one is gonna have a radius of, let's say, 50, and the other one has a radius of 60. All right, so the wall thickness of that pressure vessel is going to be 10 millimeters. That's quite a significant thickness depending on the material that we have in here. I'm going to close this. So I'm going to close it in here and in here. The reason for that is that we are going to revolve around this central axis that we have in here. We are going to take whatever drawing we have and we are going to revolve it around that axis 360 degrees, and that's gonna create our solid structure. So what I have to do is, using this tool that is called Auto Trim, I'm gonna delete these lines in here. And this is the section that I'm gonna revolve around this y-axis. Does that make sense? Yeah. All right, so I'm just gonna exit in here, sketch the section for the revolved solid. That's my section. How many degrees? So 360? No. 90 degrees, because we are gonna model only 1/8 of the sphere. So here is only 90 degrees. I have my wedge, or like my section in here, so it looks really nice, right? I have here my inner part of the structure and then my outer part in here. Let's go quickly to the meat of today, which is the material properties. All right. So far, what properties have we used? Not what material, but what properties? Only elastic modulus, right? So whatever load we apply, the structure is going to deform linearly. So if I apply 50, then it's going to deform X. But if I apply 100, it's going to deform 2X. So it's quite a linear relationship, but not everything works like that in reality. So usually, or not usually, every material has two regions. The elastic region, here highlighted in green, and then the plastic region. So those of you who I asked to start looking into plasticity, pay a lot of attention here, because this is how you do plasticity modeling in Abaqus. So what we are going to do is, once we have our yield stress, so this value in here, let me paste it in here. This value in here is my yield stress. So at my yield stress, I know what the strain value is, right? Because from Hooke's law, I can define what this value here is, right? What I'm going to do is I'm going to create like a new axis in here that is called plastic strain. And then I'm going to measure for every single point of the plastic region for a given stress what amount of plastic deformation I have. So how do you get these properties? From a uniaxial tension test, right? So for example, here, for my sigma 1, I have a plastic strain of X value, whatever value. And it's simply the difference between that particular strain minus my E0. That E0 is my strain that corresponds to yielding. All right? So basically, what I'm going to do is simply provide Abaqus all the information about my curve right after the yield stress. So as you guys see in here, what is the plastic strain right at yielding? Zero, exactly. At my stress number 1, I have X amount of plastic deformation. And then after I apply my stress number 2, then I have X amount of plastic deformation. So I have to provide Abaqus as many points as I can. You don't have to do like a lot of points, as you're gonna see here. So for us, I'm only gonna provide these 5 points. In between, Abaqus is gonna do a linear interpolation. All right, so let's enter these properties. So for this particular strain, steel, what is the yield stress? Can anyone tell me for this from this table? 246. So this table is saying, hey, right at 246, I started yielding, but my plastic deformation is 0. I'm right on that edge between elastic and plastic regimes. But when I have 0.0235 millimeters over millimeters of plastic deformation, that you reach it whenever you have a yield or applied stress of 294 megapascals. And then so on, right? And we are gonna see how this curve looks like here in Abaqus. So let me go back here, and here in material properties, let's add elastic. So my Young's modulus is 210 e to the 3. I'm gonna be working in millimeters, and my Poisson's ratio is 0.3. To add the plastic curve, I go here to mechanical, plasticity, and then I go here to plastic. And then I start adding those values. So let me bring that presentation here. So what is my yield stress? 246, and my plastic strain is 0. If I hit enter, I'm gonna add one more row. The units is megapascals, right? Because we are working in this system in here that shows that if my dimensions are in millimeters, my force is in newtons, then my stresses are in megapascals. All right, let's keep filling that table. 294, 0.235, 370, sorry, 0.0235, 374, and then 0.0935. 437, then 0.1377, and 480, 0.18. All right, I can grab this. I'm gonna just create a XY data super quickly. And then I can go here to results, XY data. And then this is how my plastic deformation looks like from that table. Imagine that from here, you have a line and a straight line that correspond to the elastic part. And then this is showing how much deformation you need after you apply stresses, right? How much plastic deformation you have in your system. This doesn't look like a curve, right? But believe me that it's something like this. It is something like this, all right? So we are just modeling or input, adding this information into Abaqus. Something to have in mind, this curve is the true strain stress curve. It is the true, not the engineering one. Anyone remembers the differences between those? One, they take into account that the transversal section changes, right? So that's the true stress. The other one, which is the engineering, they don't have the area modifications into account. So that looks more like that beautiful curve that wherever we have the yielding and then we go past yielding, we have to enter the true stress curve for that material. How easy is to find those values? Steel true stress curve. Abaqus. So what you do in here, Abaqus steel plasticity, for example. That's how I grabbed this one. Here is showing that curve that we are using. These are the values that I'm using here. So for the elastic part, we know that the elastic modulus is 210 gigapascals. And then I only added these 5 points in here. And this is our true stress strain curve. Does this make sense? We are just grabbing points from our tensile test. We grab those points and then we are inputting them into Abaqus, just so we know how to add plasticity here in our model. All right, so I already have my material. I'm gonna create one section, homogeneous, and my material number 1. And then I'm gonna select everything, and I'm gonna say that all of this part has that material number 1. Okay. Let's bring everything into the assembly. All right. And let's first create the mesh. So I'm gonna go here. Actually, let me do something. I'm gonna rename this model. So this is gonna be mechanical only. That's gonna make sense in a little bit because we are gonna do incremental steps. First, we are gonna do a mechanical analysis, which is only applying pressures, and then we're gonna add some temperature boundary conditions to our model. All right. So here in mesh, I'm gonna create a seed, as we all know. Let me see how big this seam is. Let's do something like 2. All right. Let me go here to element type, 3D stress. That works great. And let's see how the mesh looks like. It's a beautiful mesh. So it's a structure. It's a nice and beautiful mesh. It's refined enough. So I think we are good here in terms of our mesh. Now, comes the important part, which is adding the boundary conditions. Okay. So, what boundary conditions do you think that this problem has?
The edges shouldn't move.
Which edges? So this edge.
So yeah, the outer.
So these outer edges, they cannot move, right? And what about here?
Yeah,
Can this move or not? It can. So, does anyone remembers when we did trusses? If you have a symmetric truss, what do you do in the middle? You add rollers. So because this edge in here, this edge in here, and this edge in here, they correspond to symmetries. I'm gonna have to add roller conditions in each one of those. Okay, so let's do that. Let's do the easy one first. So let's go here to boundary conditions and let's call this bottom roller. So it's gonna be displacement, and then it's gonna be this surface in here. Which one should I have to click? Don't be afraid, it's fine. U2, right? Can anyone see the axis in here?
Yeah.
So that cannot go downwards. The reason for that is because I have an exactly similar piece underneath that is applying the same like action and reaction, right? So that particular edge doesn't move along that vertical axis. So that's how we apply symmetry for that particular edge. All the other things, they can move, right? So I'm gonna just leave that like that. So we have those nice rollers in there. Okay. Let's add another one. So symmetry, edge, let's call it edge number 1, which is gonna be this edge. Which one do I have to click? Where is the roller? X, right? So it's the perpendicular boundary condition to this edge. So if we look at here, we see the x-axis. So that boundary cannot move in the x-axis. So if we look at that this way, let's take a look at that this way. Let's remove this. We are adding a boundary condition to that edge, so it cannot move out of plane. And the only way to restrict that is restricting the movement in X. Is this view more clear, right? So now I have to restrict X. And now you see the dimension of the rollers. It's basically just preventing the movement in that direction. We are missing one more edge, which is this one in here. So let's do symmetry, edge 2. What is the direction for that edge? Z. Right? So we have boundary conditions in X for this edge, in Z for this edge, and then in Y. So we have boundary conditions in every single degree of freedom, so we are good to go. Remember, if you don't add boundary conditions in every single degree of freedom that you have, Abaqus won't solve it. It's not Abaqus. Any software won't solve anything, right? Because you don't specify how something is behaving in one particular axis. So you need at least one degree of freedom, or yeah, one boundary condition applied in each degree of freedom. All right, so because I said in the beginning, let's create a step. So here, a step is gonna be a general static analysis. All right, don't move anything from there. And let's apply the load. So I'm gonna apply the internal pressure. All right. Oh, no. Internal pressure. So it's here, pressure. Let's say that we applied an internal pressure of 250 megapascals. All right. And let's add a outer pressure. So outer pressure here, and I'm gonna select the outer surface. And here, the pressure, what value should I put in there?
Atmospheric.
Atmospheric pressure. I don't know what that is, but let's put something like 50 megapascals, all right? It's super small, but it's, let me see, it's, so this one, 0.1 megapascals.
Wow, yeah, that's keeping you down at 50 megapascals.
Yeah, it's okay. So right, we have a really high internal pressure for this pressure vessel, and outside, let's do the atmospheric pressure, which is 0.1 megapascals. So here, 0.1. So now we have outer pressure in that surface, and then inner pressure in there. Are we missing something before I submit?
No, we got mesh fire conditions materials.
All right. So let's create a job in here that is gonna be called mechanical only. All right. Let's write input. I'm gonna show you something cool. All right. So here in my desktop, if I can find it, here, Abaqus 3D Plasticity. I have my input file already. Do we? Write input. Let me see. Abaqus 3D modeling. Yeah, I have in there. So sometimes, whenever you have to submit several runs, you cannot do them from the CAE. So you start using something that is called the command line. Anyone knows what a command line is? So like terminal in Linux, like hardcore coding, if you want to call it like that. It's a way to communicate with the computer just through like commands, right? Instead of just clicking as we do in here in Abaqus. You don't have to do this. What we could do here is just right click in here and then submit. But I'm gonna do that from the command line, all right? Just for fun. So what I'm gonna do here is type here CMD, and that's gonna show me the command prompt, all right? So what I'm gonna do is change my directory, which is that CD, right? And then I'm gonna paste my folder location. Now I'm in that folder, all right? If I want to see what's inside that folder, I type dir, and then it's showing me that I have this file that is called mechanical-only.imp. IMP is the format for Abaqus for input files, and that's 828,000 bytes. That's the information that it's giving me. How to run? So I'm gonna do the following command. Abaqus, the job. What is the job name for this problem? So let's call it mechanical only. Because we're running now in 3D, this is gonna start becoming important. So we are gonna do CPUs equal to 4. So we are gonna run this problem in parallel. So the solution time is gonna be a little bit faster. And this int is just, that is a flag, if we want to call it like that, that is called interactive. So Abaqus is gonna show me here in the screen whenever it is completed. All right, so it's more like an interactive way to access Abaqus. I'm gonna hit enter. And it didn't work. I think we cannot run in OneDrive. Let me see. So let's do it again. Abaqus, job, mechanical only, CPUs equal 4, and then interactive. Unfortunately, we cannot do it from these computers. But okay, if you type that command in your machines, then it's gonna work. All right. I just wanted to show an interactive way of running Abaqus, but it doesn't work with OneDrive. Let me try once more. Abaqus job equals mechanical only interactive. All right. We cannot run in parallel in these machines. Why? I don't know. But basically, I just removed the CPU's flag that I had. All right. So Abaqus is running here. So it's telling me, hey, out of 400 licenses that we have here on campus, you're using 25, or there are 385 left. I'm running this job in here. This is the license server. Here, Abaqus, the pre.x is just reading the input file, and now it's running. So whenever the run is completed, Abaqus is gonna say completed or error. But look, I submitted this job like 40 seconds ago, and it's still running. So imagine the solution time if we were to solve the whole sphere. And this is a really coarse mesh. All right, so 3D, awesome. But if you can avoid it, right? Because if you get the same results by supposing that everything behaves in 2D, it's fine, right? But some things, they cannot be modeled as 2D. So you need to do some 3D modeling, right? But it's always good to know all of them. It's still running. Here, if I check my folder here, it's showing me that it has created a lot of files, but it is still running.
I got mine just by going to output database and then loading it up.
Yeah, but it's probably not completed yet. Yeah, I can access this status file in here.
So is this limited by the computer or by the program?
Yeah, the computer. These computers are not like really fast. So here, out of the 1 second that it, so what happens now? Abaqus, you guys remember when I requested reaction forces, right? Or for the tensile test homework, how many points you had? 2, right? The initial 0, 0, and then the final, which at this load, you get this amount of displacement. Here, Abaqus has to break the load, the pressure that I'm applying, into small increments. And the reason for that is because once you achieve yielding in your structure, then you have to start adding the load little by little, because you have to recompute the amount of plasticity for each time. So it's an iterative process, and that's why the simulation is taking so long. It's taking a long time. Yeah, mine's still running. Okay, 7:43. I guess we can access the results now. So let's go here to results, out of the database, and then I'm gonna open the mechanical only ODB file. Let's check the results in here. Fun misses. Let me see. Fun misses. Yield. Let me see. Fun misses in here. All right. So what is showing in here is that initially, this is how the deformed configurations looks like once I apply the pressure, like a little bit of pressure. Then a little bit more, a little bit more, a little bit more. And then you see how the stress here in the inner part starts increasing, right? As I apply more pressure, the stress starts like to distribute throughout the structure. Then more. And then here, basically what this is saying is it's too big of a stress, right? So how do I know if my structure is yielding or not? You go here to AC yield, and that's going to show you the elements that are undergoing yielding. So initially, nothing is going under yielding. Nothing is going under yielding. Actually, everything is under yielding. Let me look at this. Equivalent plastic strain. All right, yeah. I think we applied too big of a stress in here. All right. So here, PEEQ, that's the plastic strain that we have in our structure. So as you can imagine, we have more plastic strain near where the high load is applied, and the plastic strain starts decreasing as we go away from the structure. But here, the load was way too high here, but so everything is undergoing yielding, right? Because this value in here, 5.29, corresponds to the blue color. So that blue color, which is even in the outer part of the structure, is also yielding. Okay, let's kill this. All right, let's see here. This is still running. Okay, let me cancel this. All right. And let's add heat transfer to this problem. All right. Who is trying to add heat transfer to the project? You. All right. All right, so let's do something. Let's copy this model. All right, so I'm gonna copy the model, and then it's gonna be thermal mechanical. All right, let's modify the material. So let's go here to material, and I have to add some heat transfer conditions, or sorry, properties to this in here. So I have them right here for you. Heat transfer, CP. Anyone remember what CP is? Specific heat. So I'm gonna go here to thermal. I'm gonna go to specific heat, and then I'm gonna enter my specific heat for the steel. So it's gonna be 420. But then my properties are in joules, kilograms, Kelvin. Kelvin is fine, even though that I'm gonna apply the temperature in centigrade. This CP, the delta, it doesn't matter, right? This could be Celsius as well. They are the same in different unit systems. However, my kilograms, I have to transfer those to ton, right? So to do that, to go from kilograms to ton, I actually think this is, yeah, this is 420, yeah, e to the 9. So this e to the 9 in here. My density, I'm gonna go here to general, to density, and my density in these systems is kilograms over metric cube. I have to convert to what? To ton over millimeter squared. So if we do that conversion, we end up with this value in here, 7.750 e to the 9. So basically just move the dot 2 points to the left and then add this e to the 9 in here. So 7.75 e to the negative 9. The conductivity, 50. We don't have to change that one. All right. Watts over meter Kelvin. That can stay there like that in here, because if I change the watts, I also have to change the meters. So at the end, this is gonna be the same as 50 over centigrade millimeters. So we don't have to change this one. And then the expansion coefficient. I'm gonna go here to mechanical, expansion coefficient, and my expansion coefficient is 10e to the 6. Sorry, 10e to the negative 6. So that's my expansion coefficient for steel. The hardest part of these problems is to find the properties and add them in the correct values. So here, I can go Abaqus units heat transfer. So in several tutorials, like this one in here, like this one in here, let me show you where, not this one. Okay, so it shows some examples on how to do that. So we are using the SI millimeters values. So the pressures is in megapascals, the gravitational constant. Here, they have the example of steel. So we went from kilograms to meter cubed to ton over millimeter cubed, right? Then, yeah. Basically, the way I do this is that I go to a paper. For example, I search for heat transfer Abaqus and for a particular metal, and that's where I grab the properties from. All right, let's not go into too much detail there. So I already added the thermal properties. I'm gonna change the step, all right? So here in step, I'm gonna remove the step. Actually, no, I cannot delete it. Yeah, let me delete the step. And then I'm gonna create another step. Now, it's gonna be here, coupled temperature displacement. All right? So I'm gonna click that one. Here, we only care about the steady state, right? We are not gonna do heat transfer where like you see the heat going through the material and how it reaches the outer boundary. We only care for now about the steady state, which is the final state in here after you have applied the thermal conditions for a long time. So after you apply the boundary conditions from heat transfer, and then the system is in equilibrium. So that's what a steady state means in here. All right? So I'm gonna select this one. The response is gonna be a steady state. And I'm gonna go here to the mesh. So I have changed two things so far, actually three. Material, I added thermal properties. A step, I changed from static general to coupled temperature displacement. And I'm gonna have to change the mesh. And the reason for that is I have to select in here in part, I'm gonna select everything. And now I'm gonna select here coupled temperature displacement. Okay? If I don't do that, Abaqus won't run. So in the element type, which again, we access that element type through here, I select everything, and then I say, hey, these elements, they have to be corresponding, or they have to correspond to the analysis type that I'm running here, which, as I said here, is coupled temperature displacement. Okay. The boundary conditions, they are still valid, right? Because we are doing some mechanical loading. So if I revisit my loads and everything, I got my loads erased. And the reason for that is because those loads were applied in the previous step definition that I had. So I just have to apply those loads again. So let's do it. Inner pressure. So I'm gonna select this surface in here, and I'm gonna say that the pressure magnitude in there is 150 megapascals. And actually, let's do something way smaller. Let's do 10 megapascals. And then the outer pressure, we already said that it was the atmospheric pressure, which is 0.1 megapascals. All right. So have I added some temperature here? No. So let's do the simplest case, which is a conduction analysis, right? So what I'm gonna do, go ahead and do is, here in boundary conditions, we always use mechanical. So what I'm gonna do here is go to other, and in other, I have this temperature boundary condition available. So this one, I'm gonna call it inner temperature. And it's gonna be for this surface. And internally, let's say that the fluid that is under a really high pressure is also under a really high temperature as well. So 150 centigrade. All right. And then let's add the outer temperature. And for the outer temperature, this outer surface is going to be an ambient temperature, which is going to be 25 centigrade. For those of you who are not very used to that unit system, is 150 centigrade to Fahrenheit. That's going to be the internal temperature of our vessel in here. All right. Let's see if this runs. All right. So let's go here to create, and then thermal, mechanical. All right. Let's see if Abaqus allows me to do some parallelization. So let's use multiple processors. So that the way I access that is whenever you have this window from job, you go here to parallelization, and then you select this to allow the model to run a little bit faster. And let's submit this. And let's monitor. So here in the monitor, when do we know that is ready? Because here the increment has to go from 0 to 1. And Abaqus will break the pressure into small linear increments. So initially from 0 to 0.05, from 0.05 to 0.1, and small linear increments until the totality of the load has been applied. Let's see if this runs. So warnings, absolute 0 temperature, so that one doesn't matter a lot. And completed. Wow. Let's go to results. Okay. So let's try to understand what's going on in here. NT11. NT11 is nodal temperature. That's how Abaqus shows you the temperature. So we said internal hot, outside cold. Let's see if that's actually true. All right. So we have an inner temperature of 150 degrees, and my outer temperature is at 25. Then, because this is linear, we're going to have a linear gradient from the inner surface to the outer surface. All right. Let's see what other outputs we have in here. HFL. So we can go here to Abaqus outputs variable list. Here to the first one, and then let's search for HFL. Current magnitude and components of the heat flux vector. So if my temperature is here in the inside hot and in the outside it's cold, how do you think that the heat flux is going to look like? Where is where is all the flux headed towards? Outwards. So the outer part is going to be receiving more flux, right? Because it's the colder part. Remember that the heat transfer works from hot to cold surfaces. So my cold surface is going to be receiving a lot of heat. So the heat flux in my cold surface has to be really high. Oh, it's the other way. Oh, why? This doesn't make sense. Okay, so it's not like a set it, it's from where the heat is transferring, right? So my inner surface is really hot, so that means that most of the flux is traveling from that surface, all right? My outer part, that outer part cannot create any flux, right? Because it's mostly receiving anything. So that's why the flux here is so low, all right? Makes sense in terms of the heat transfer? What else do we have in here? Plastic strain. So let's search here in our Abaqus keywords what PEEQ means. So PEEQ, equivalent plastic strain in the elastic plastic network. So similar to von Mises. Von Mises stress, what it's doing is taking all these stresses in my structure, and then it's puts all of those values into a single scalar value. And that value decides whether my structure is yielding or not, right? Plus PEEQ is similar. Abaqus is taking all the strain components, so a strain in the one direction, a strain in the two direction, a strain in the three direction, the shear strain, so epsilon 1,2, epsilon 1,3, and epsilon 2,3, and it's putting all of those values into a single value, which is this PEEQ. So basically what this is doing is showing in your structure where you have plastic strain. So let's take a look at that. PEEQ. We don't have any, all right? What does this mean? We are not going past yielding with that pressure and those heat and those temperatures that we applied in here. So let's increase the pressure a little bit so we can see some yielding in our structure. So my inner pressure, I'm going to increase it from 10 megapascals to 50 megapascals. And let's submit it. So for those of you that I mentioned, hey, let's do a parametric study on the load. I've gotten some questions about that. This that I'm doing right here is a parametric study on the load. I just varied the load from 10 to 50. So if I go to 50 megapascals and then I see that all my structure is yielding, then I decrease the load a little bit until I find the more or less a ballpark in which the structure starts to yield. All right. So completed. So let's take a look here at the results. And let's take a look here at the equivalent plastic strain. All right. We have some yielding in here. Let's take a look here at AC yield. So yeah, we do have some yielding here in our structure. Let's take a look here at the von Mises stress. Did I change the outer? No, so inner 50 and then outer pressure 0.1. Now that is correct. All right. Now the results are a little bit counterintuitive, right? Because I applied a high load in here, but then I also have a high temperature gradient with my thermal expansion, and that's causing the outer surface to be under a lot of loads. So if you apply some loads and then you add some thermal loads, the behavior of your structure might change completely. before we do a simple problem, anyone has questions with how to add plasticity to Abaqus? No. Let's do a quick, and this is gonna be recorded for you. Let's do a quick 2D analysis of a plate, so we see some necking in our plate from the plasticity. So I'm gonna do that flying, all right? So I'm gonna go here to model 3, part, it's gonna be 2D planar, all right? So it's gonna be minus 50, minus 50, and then 50, 50, all right? I'm gonna add a hole in here, so 0, 0, 0, 5, all right? I'm gonna create a material. Let's see if I can copy the material from here. So material library. So I'm gonna steal that material. So let's create a library, material, library. And then I'm gonna add that material in here. So I just created a material library, right? Because my previous models, they had some materials in there. So I'm gonna say, hey, my material library, I'm gonna steal your material number 1 from your thermomechanical model. And then from my model number 3, which is the one that I'm creating, I want to have that material available as well. If we see here now, my model number 3, I now have the material number 1 that I created in those models. And if we check here our working directory, somewhere here, we must have a material library. Okay. So I have the material number 1. Let's review it again. So elastic, 210 e to the 3, plastic. I have my tabular values in here. So let's quickly create a section. Let's apply the section in here. Let's bring everything into the assembly. Sorry if I'm going too fast. I just want to show you the results, and still this is gonna be recorded. A step. I'm just gonna do a static analysis in here. I'm gonna have some boundary conditions in here. So this, I'm gonna have that this bottom surface is gonna be restricted. And then in this top surface, I'm just gonna apply a displacement of 5 millimeters. So I'm just gonna pull that surface 5 millimeters, all right? Let's go to mesh. Let's create a seed here. Apply. So this is kind of small, so let's do 2. All right. As we said before, let's do the circle a little bit more detailed. So let's do 0.5.
Just to confirm, you'd like to call Maria Elena Ramirez?
Sorry. And let's mesh the part. All right, that's a beautiful looking mesh. Refine here in the circle, and in the other parts, let's refine. Sorry if I'm going too fast, but this is gonna be valuable information for you guys. Let's create a job, and let's do plate, plastic. All right, and let's run it. Let's go here to monitor. It started. Where do you think that this is gonna start yielding? It says stress concentration. Nice. So now, instead of having a single increment, look the way that Abaqus is applying the load. First, it applied 0.05% of the load, then 0.05, and in here, Abaqus stayed for a while. right? Trying to apply this load. And the reason for that is the solver didn't converge. So this is a really complicated problem. Even though that it doesn't look like that, it is a complicated problem. So Abaqus found the convergence in here, and then, okay, now I know how to apply 15% of the, sorry, 1.5% of the load. I can apply a little bit more. I'm gonna apply 1.6% and then 1.75. So Abaqus is incrementally applying the load in here because the theory behind this plasticity model that we are using is called incremental plasticity. All right. As we start yielding, we cannot apply the load like that because we don't have a linear relationship, right? So we have to break and let's try to be within like this behavior in here. So because this is a nonlinear behavior, I have to apply that load in a nonlinear way, which is just break it into smaller increments. Abaqus is super smart. So Abaqus knows how to break and converge super quickly. For some problems, it doesn't work like that, and then you have to tell Abaqus how to break the load. But for these simple, complicated, simple cases that we are covering in here, you can let Abaqus take all the credit, all right? So right now, completed, right? This one in here, the frequency here means that 100% of the load has been applied, all right? So let's take a look at those results. Don't get scared. This is going to look ugly. Do you think that this works like that in real life? Yes, it does. It looks like this. So if you have this plate and you start pulling it, it's going to look like that. So something cool that we can do in here is do this video. So here, we don't only have one final deformed configuration. We have the history for the whole application of the load. So we go here to frame selector, and then we can start like playing this like in a movie. So you can see as we keep increasing the load, how this whole start expanding like that. And adding a lot of plasticity. Let's take a look here at the plastic strain. This butterfly effect is widely known. It's everywhere. So if I put here crack plastic strain zone shape. Does it look like something like that? And this has been proven experimentally. So there's some way of tracking like your tension specimen, and then you can like plot deformation on top of that. So you can do that experimentally with something that is called DIC analysis. So DIC analysis, tensile test. So basically what we do is we put some speckles on top of this sample, we stretch it, and then using some software, we can know what the plastic deformation looks like on that sample. And that in that way, we have verified, we know, they have verified that this is how the plastic strain zone looks if you have a stress concentrator. And we have indeed a stress concentrator in here. So what's gonna happen in the next few classes? We're gonna go a little bit more about this plastic modeling here in Abaqus, because this was a really quick introduction. But then we're gonna add a crack. And that crack is not only gonna open, but it's gonna start propagating throughout our mesh. And that's gonna be beautiful. And that's really advanced modeling here. So I'm giving you finite elements in a different way, not focusing on the modeling, right? Because I know that each one of you guys is capable of adding, or eventually you're gonna get it done, like in terms of creating a complicated shape. But what's important is how to add the physics, right? How to add the plasticity, how to post-process the information that Abaqus is giving you. Because if you input trash, you get trash, right? So we want to be smart users and not only add some crazy properties and get our result. We want to really get a good insight about the problem in here. Eventually, you see this point where like it went from being expanded to like keeping going back. At that point is where like fracture should happen, but we don't have fracture in this problem. So whenever we reach a certain amount of plastic deformation, then we are gonna say, hey, that element that is going on, undergoing a lot of plastic deformation, just remove it from the mesh. It's not useful anymore. It's no longer capable of holding load. And that's how we start doing the crowd propagation. Interesting?
Yeah.
All right. We could also add some heat transfer to this, but yeah, it's as you guys saw, it's super simple. What else can you do in heat transfer? You can add convection, right? So for those of you who have had like this thick pressure vessel, you want to see, hey, what happens if I have that pressure vessel in a ambient temperature that is super cold? I have it in a fridge. So you have your fridge temperature, and then you have this surface, and then you can see how much that air or cold air is affecting the results of your pressure vessel, and things like that. All right. Or also, you are creating a combustion, right? So the gas inside your pressure vessel is at a really high temperature. Then you consider that as your ambient temperature, and then you add some convection between your inner surface and then the air that is really hot inside your pressure vessel. So a lot of things that we can start adding here, but as I said, quick introduction showing a lot of capabilities, but then we're gonna focus a little bit more on the things that I do, which is fracture assessment for structures, all right? Again, if someone wants to give me an update before Wednesday, shoot me an email, or if someone needs more help, all right? Thank you guys for coming.
I sent you my email.